Welcome to the first learning control seminar. So the goal of this seminar is we want to basically cover a very broad topic in learning control. It includes, but not limited to, reinforcement learning, learning for dynamic system, optimal control, MPC, interactive decision making, robot learning, embodied intelligence, a lot of topics. And if you like this seminar, please help us advertise it. So it's going to be bi-weekly. And if you want to present your research, feel free to register in the Google form. And I'm applying for some refreshment, like basically free food, but no guarantee. I will try to get us some refreshment from next time. Okay, today we're very excited to have Gokul Swamy here to present his research on efficient reductions for interactive learning from implicit human feedback. So Gokul is a fourth year PhD student in RI at CMU, and he is co-advised with Drew Bagnall and Stephen Wu, and his research centers on efficient algorithms for interactive learning from implicit human feedback, such as imitation learning, RL from human feedback, aka RLHF, learning with limited state information, and build on techniques from RL game theory and causal inference. And he has spent summers at Google Research, MSR, NVIDIA, Aurora, and SpaceX. And he got bachelor and master degrees from UC Berkeley. Okay, without further ado, let's welcome Gokul to start his presentations.
Thanks. Let's see if I can share my screen yet.
Oh yeah, it works.
Perfect.
Thanks.
Awesome. Second. Then I'm going to. Okay, can somebody on the Zoom confirm they're seeing this screen? Okay, cool. Hello, hi everyone. If we haven't met before, I'm Gokul. And today I'm gonna be talking about a few projects I'm really happy about. I think they might seem a little bit disparate at first, but I think there's like kind of underlying interesting kind of algorithmic principles that I kind of want to kind of share. This is a really long and rather pretentious title, but I'm going to be trying to, at heart, get at algorithms for learning when you don't have access to reward information. So in essence, when you get things like demonstrations, preferences, things like this, but you still want to be able to actually be able to do policy optimization. That's what sort of implicit feedback here. Interactive learning here means that we're actually going to be interacting with the environment in some way. We're going to actually, try things out, see what happens. That's going to be pretty important. And efficient reductions is really more kind of the style of algorithms we're going to be talking about. I'm not going to be doing sort of like very sort of careful finite sample analysis or anything here. I'm really just going to be talking about kind of high-level algorithmic principles that are important. I should mention this is joint work with my advisors, Drew Bagnall and Stephen Wu, my long-term collaborator, Sanjay Chaudhary, a superstar undergrad, Jun Tao Ren, and some folks from Google, Alec, Chris, and Rahul. So I should also note that I am usually fairly bad at timing talks. So this will probably go a little bit over. If you have to leave early, I'm not at all offended, but that also means that if you have questions, just please ask them in the middle. Don't wait till the end. So let's go ahead and get started. So broadly speaking, I'm very interested in these problems of trying to learn how to make sequences of decisions. This ranges from things like autonomous vehicles to content recommendation in social media to the sort of growing set of large language model chatbots. And I think when you think about these sort of problems, oftentimes they're very, the systems you're trying to learn have to interact with people in a very kind of closely coupled way. And for these sorts of problems, the metric you're trying to optimize, or the thing you actually want, is to act human-like in some way. And it's often very, very hard to write down a function that captures exactly what that means. Something like driving, right? If I asked you to write down the exact function you were optimizing while you were driving, that'd be pretty hard. You could probably tell me some things that mattered, right? Like I care about staying in the center of lanes, respecting speed limits, things like this. But just writing down a function we can optimize is really, really hard. And kind of when we continue to sort of build these systems and kind of deploy them more and more widely, this fact that they really have to interact and act around people in a way that is reasonable ends up being really, really important. So I'm going to be talking about, two different ways that we can actually try and learn such functions and optimize them. The first is going to be from demonstrations. This is usually called imitation learning. And the second is going to be from preferences. This is often called RLHF, or reinforcement learning from human feedback. I'm going to start off by talking about imitation learning. And so with apologies to my advisor who runs a self-driving car company, I'm going to give you guys a crash course in imitation learning. So what we're going to do is we're going to get data from some people who are good drivers. We're going to strap them in these cars. We're going to have them drive around, Pittsburgh. And then what we want to do is learn a policy that lets the car do the same thing. Okay, that, isn't in of itself a fairly hard problem. So I'm going to scope it down a bit. I'm just going to focus on learning to be able to drive laps around this track. And let's say we get some sort of expert demonstrations here in green. They're basically staying in the center of the lane, kind of acting pretty reasonably. And let's say we featureize our state with something like our X, Y, and our heading, and then have our actions be, how much we're turning the steering wheel, how much we're pressing the brake pedal, things like this. So we have, these kind of two streams of data. And I think the most natural way to try and solve this problem would be purely via supervised learning. So we would just regress from the collected states to collected actions. And you could use some sort of like mean squared error criterion for this. I'm just trying to minimize the difference between my predicted action and the actual action that expert took in that state. This is usually called behavior cloning, somewhat pretentious thing. It just means supervised learning. So this is, I think, a pretty reasonable way to first try and solve these problems. It should be your first approach. But fairly often when you try and learn a policy via behavior cloning for a kind of complex task like driving, you'll notice that when you actually deploy your policy in the real world, it'll go off the rails pretty quickly. So what's happening here is that, early on in the trajectory, I make a small mistake. I end up in a situation where I don't have data. I don't know what to do. I make another mistake, and this just keeps happening over and over and over again. This is sometimes known as compounding errors. And I think that a slightly more formal way of thinking about this is that we're effectively in a situation where we have covariate shift. So the sort of input distribution, our state distribution is what's changing here. So we trained here purely on states from the expert state distribution, but then at test time, when we actually roll out our policy, we're being tested on the learner's induced state distribution. And this sort of shift can lead to kind of unfortunate outcomes. So if we sort of like maybe pause and think about that point for a second, covariate shift in general is a really, really hard problem to solve in machine learning, right? Like if I test you on an input you haven't seen before, how are you supposed to know what to do? But I have just like one trick in this talk. I'm going to use it over and over again. And it's just this. It's that interaction allows us to generate samples from the test distribution. What this means is that I can actually, drive my car in the real world in my good simulator, whatever. I can see that, when I turn left, I ended up here. So I can actually sample from my own induced state distribution at test time. Now, once we have sort of access to this data, the whole game becomes, how do I then use this information to actually do policy optimization better? And I'm going to talk about one approach for this that I'm a particularly big fan of, called inverse reinforcement learning. If I was more clever, the letters between those things would have actually matched up, but it was still a pretty cool transition. So we're going to have our set of, learner states and actions from doing a rollout, and we're going to have our set of states and actions from the expert. And we're going to basically do the most natural thing here, which is try to minimize some notion of divergence between them. So the way I like to think of this is effectively a GAN, but in the space of trajectories. So our generator here is a policy coupled with a world model to actually give us, trajectories in the real world. And our discriminator here is basically trying to differentiate between expert trajectories and learner trajectories. So the way game solving occurs here is I do reinforcement learning with this discriminator as my learn reward function, as my policy update. And then for my discriminator update, I basically try and just classify between the expert data and the learner data. So it has a very similar flavor to like a GAN. The difference here is that rather than doing supervised learning for the generator update, I'm doing reinforcement learning because it's sequential decision making. So that's sort of like a kind of cartoonish picture of how this usually works. You can state this slightly more formally as sort of equilibrium computation. So we're going to have some expert policy pi e, we're going to have our policy pi. And let's say we use J here to basically denote the value of a policy under some reward function F. What we want to do is ensure that under like the worst case reward function here in this class F sub r, we're able to find a policy that is close to the expert. So what this means is that no matter what reward function we actually would be tested on, i.e. whatever reward function the person has in their head, we still ensure that we're doing well, because we're doing well, I guess, across all the possible reward functions. In essence, a lot of this sort of imitation learning essentially kind of boils down to solving this 2-player 0-sum game in different ways. So I'm going to now talk about algorithms for actually solving this game. But before I do that, does anyone have any questions about this high-level framing?
Question.
Yeah.
Why is pi?
Yeah. So I guess so pi here is
The minimum pi is behind maximum. So your maximum length is done first.
Oh, I mean, assume the minimax theorem holds here, so it doesn't matter which order I do it. Sorry. We know from like von Neumann's minimax theorem, right? Like if this is, let's say this is convex, and this is convex, and this objective is convex as well, I can swap the order, right? Yeah. Yeah, I'm going to assume all the natural conditions for specifically Sion's minimax theorem hold here. Good question. Other questions? Cool. Okay, so that's the thing. Let's maybe kind of look at the kind of pros and cons of this. So the first, I'm not going to do a proof for this, but this sort of inverse reinforcement learning approach is robust to compounding errors. This should be intuitive because I can't get surprised at test time about what states I end up in because I'm continuously rolling out and seeing where I end up. But the sort of like downside of the inverse RL approach to imitation, right, is that you require repeatedly solving a hard exploration problem, right? Like if you think about what I just suggested we take the easier problem of imitation learning and reduce it to repeatedly solving the hard problem of reinforcement learning. So at every single iteration of this procedure, I'm solving an unstructured search problem over and over again. So this is, not great. Let me give you a slightly more visual example of this point. So let's say we think about the learner, sort of operating in this sort of binary tree structured MDP. This means that we start at the top, and at each time step, they can go left or right. And let's say we constrain the adversary here to basically pick the word functions. There's 0 everywhere in the tree, except somewhere at one of the leaf nodes. And let's just say for the first iteration, they pick this one. And it's pretty easy to figure out what pi star is here, right? It's going left at each time step to get the reward 1 there. But if I wanted to actually compute this policy, right, what would I have to do? I would have to explore every single leaf node in this tree, right? And if my tree is of depth h, this means I have order to the h leaf nodes. So already on the first iteration of my procedure, I'm already playing exponentially in the task horizon. Okay, but then we do this again, right? Let's say the next iteration, I pick this reward function. What I'm going to do then is, have to compute this optimal policy, which means I once again have to look at every single path through this tree. Depth h again, I'm again playing for to the h. So the way I like to think about this is that we're effectively trying to play a game of like adversarial whack-a-mole with an RL hammer. We're repeatedly just picking a random place for the mole to pop up, or our adversary is, and then we're trying to use a really, really computationally expensive hammer to actually solve it. And as you can probably tell from the relative size of this hammer to this mole, I think we're using a bit too heavy of a hammer. And I'm going to be talking about today how we can, in essence, have a lower computational burden while still achieving strong guarantees. Cool. So, and I think, the question I essentially want to try and get at this part of the talk is, how do we reduce the amount of exploration performed in inverse reinforcement learning? And there's an answer here that I think in hindsight is kind of obvious, but I think has some like subtle and interesting consequences. And it's that we can leverage the expert demonstrations during policy search, right? Notice nowhere in any of the figures we just went through that I actually look at what the expert did when I was computing a policy, right? And if I'm specifically picking reward functions that make the expert look better than the learner, this seems kind of like an odd thing to not do. Yeah.
In the talk, are you assuming the transition dynamic is not
To
solve the inner loop, the policy optimization with reward, you need to know the
yeah. Right. So I'm not assuming it's known in closed form, but I'm assuming I can sample from it.
Gotcha.
So like trace model access. So okay. So let's say that this is our we bring back our thing here, and let's just say I tell you that for this particular word function, the expert happen to go left everywhere here, right? If I tell you this, right, even though there's some reward of 1 here, right, I don't actually need to look at any policy that goes over there, right? My goal is just to imitate the expert. I don't need to be repeatedly doing this whole exponential search. I don't really need to look over there because I know the expert took this left, left, left thing. I don't need to look over there. I don't need to look over there. I really need to look at policies that look kind of similar to this leftward path. And this is really sort of the key idea. And it's that we don't need to compute a best response via reinforcement learning. We just need to compete with the expert. So that is a little bit informal. I'm going to make it slightly more formal now. So I usually hate putting proofs in my talks because I think they're often not helpful, but it took me a year to come up with this proof, and it's like 5 lines long, so I feel like I've earned it. But what I'm going to talk about is effectively a weaker notion of policy optimization we need, and then I'm going to argue that even with this weaker notion, we're still able to learn well. So specifically, I'm going to define an expert relative regret oracle, or error for short. And what you need to think about that is basically it's an algorithm that looks at, some sequence of word functions, use policies, and it satisfies the following guarantee. So what it says that is on average, under the reward functions that were chosen, I have a bounded performance difference with respect to the expert. And the reason this is interesting, right, is that nowhere in this definition did I actually ever need to compute a best response to an FT. I didn't need to actually solve the RL problem under FT, right? If I did that, then this would be true, right? Because I can only do better than the expert if I were to do that. But this is like, in some sense, doing something more expensive than required. And I'm going to argue that this particular thing is actually all we need to do to have strong performance guarantees. I'm then going to tell you a bunch of ways to efficiently ensure that this is true. But the sort of overlying framing here is that I'm ensuring that I'm just good relative to the expert. I'm just competing with the expert rather than the optimal policy for this adversarially chosen award FT. I'm going to flash one other definition here. This is just the way we're going to be selecting rewards. If you've seen like online learning before, this is very standard. This is just a definition of an online linear optimization oracle. If you haven't, it's just a very minor requirement, like gradient descent satisfies this property. So the proof here, I think, is really, really kind of cute. So it basically looks like this. I'm going to look at the performance difference between the expert policy and policy down to the word function R. I'm going to break it up into this sum of t terms, where each t is a separate of the sequence of t policies I've computed, just by linearity of expectation. Then what I'm going to do is upper bound the performance difference by picking the worst case reward function in this function class. So I'm assuming the true reward functions in my function class. Then what I'm going to do is basically look at the difference between this f star and the actual f's I chose. That is just the regret of my reward selection algorithm. And then the term that's representing here, this is exactly the regret thing that I wrote down on the past slide. The difference between my computed policy and the expert policy under this adversarially chosen reward. So this is a fairly abstract proof. If you haven't seen this sort of stuff before, don't worry about it. I don't think it's super important to remember, but conceptually you should think about there is some sort of underlying mathematical framework that is going to inspire all the algorithms I'm going to discuss. So I think after I kind of go through that proof, the natural question is, okay, what algorithms actually satisfy this property? I'm going to give you 3 examples. The first is going to be what I'm going to call expert resets, or resetting the states from the expert state distribution during RL. Second is going to be what I'm going to call hybrid training, by which I mean training your Q function on a mixture of learner and expert data, kind of a half and half mixture. And the third is going to be hybrid model fitting, which is going to be fitting a model on a mixture of expert and learner data and doing model-based RL with that model. And we have like somewhat corny acronym names for each of these that are our methods that use this sort of flavor of things. So let's maybe start off with the first one. And if you have a background in RL theory, just to be transparent here, I'm effectively like each of these algorithms is effectively minimizing a different upper bound on the performance difference. And the one I'm going to be minimizing here is the kind of classic like Jean Cockaday and John Langford style performance difference lemma. So let's go back to our favorite tree here. And let's say I tell you that the expert, visited that state and that state and that state in order. And the sort of key idea I'm going to do here is I'm going to use dynamic programming to compute a sequence of policies without doing an exponential search. So let's first think about maybe the second to last time step here, I3. And here, right, all I'm going to do is figure out if I want to go left or right, a single choice. And here, right, I know that if I go left, I get reward 1. If I go right, I get reward 0. So I'm going to go left. I'm going to lock in this policy. Then I'm going to back up a time step. And I'm going to kind of try and figure out again which left or right action I should pick. But then I'm going to execute this cache policy after this. So I would say, okay, if I go left here, I'm going to go left again, I reward 1. But if I were to go right here, I would go left again, and I get reward 0. So this means I should pick going left. I'm going to lock in this policy. I'm going to kind of do this all the way up the tree. And there's h iterations of this procedure, where h is the depth of the tree, and each iteration takes an amount of interaction that's linear in the horizon. So overall, this has, kind of polynomial interaction complexity rather than exponential. So this is actually quite nice. It gives us the first polytime algorithms for this problem. So the variant I sort of just described was this, where basically I'm trying to match these like one-step things backwards in time. This is in contrast to standard adversarial that is trying to match the whole trajectory distribution, so you have to pay for exponential search. Turns out it's equivalent that rather than doing this sort of like, sequence of things backwards in time, you can instead basically just pick a random time step and reset to that. This one is kind of nice if you have a short horizon problem, but if you have a long enough horizon problem, you probably don't want to learn like 1,000 policies. So the random time step reset usually works better. So, we've tried these out on various problems. I'm going to just present some mediocre results for now. So here, you should think of each of these as just some sort of continuous control environment. The x-axis, the amount of interaction, the y-axis, the performance. This is the performance of a pure kind of offline behavior cloning algorithm. Green here is the performance of the expert. And you should think of the gray line here as the performance of like a standard inverse reinforcement learning algorithm. I'll note that this is like a really, really strong baseline as far as adversarial goes. This is probably better than most people's actual algorithms. So like any like improvement over this is kind of non-trivial. And you'll see that just by basically running the same algorithm, but just training the reset distribution to be the expert reset distribution, you see sort of consistent improvements in performance. And what you'll also note is that as the environments get kind of harder and sort of increase them in like increasing order of exploration complexity, you see larger and larger differences. So really, we're helping kind of tamp down on this sort of like extra exploration. So before I maybe talk about other algorithms and stuff like that, any questions on this kind of high level picture? Yeah.
Hey, Go, can I understand the filter as a software version dagger? Like you query the expert only for reset, closer to the state.
Yeah.
Rather than asking for the labeling the whole dagger.
Yeah, so it's almost like the kind of the opposite of dagger in a particular sense. So here I don't need a queryable expert. I just need to access the expert state distribution. So I just need the demonstrations.
Right.
And I have to be able to reset you to an arbitrary state.
In this expert distribution.
Yes. Right. So I don't need a queryable expert. It's not like dagger like that. So in essence, you're like, it's like this is like rolling in with the expert versus dagger is like rolling out with the expert in a certain sense. Yeah. Yeah.
So you need a simulator to allow for the arbitrary state.
Exactly. Yes.
But in many simulators, there are many internal states that are difficult to set. And how do you deal with this kind of
12 slides. I think we'll be there. Yeah. That is exactly, I'm happy you asked that question. Like that's the question that when we finished this paper I had, which is like, this is a really natural idea if you can do simulator resets, but if you can't, what do you do? I'll note that I think this is a really natural idea actually in the space of language models, because generating from an expert reset for a language model is just generating from a prefix, right? That's actually a very natural thing to do there. Other questions? Cool. Yeah.
You have the task where the expert policy is not the optimal policy.
Good question. So I'm not using kind of dealing with suboptimal data in this talk, but I will say that all the algorithms I'm discussing here actually work really naturally with suboptimal data. This is a thing we're actually like using for some real robot experiments we're working on now. So I need a small amount of expert data to actually pick the reward function, but I can make my reset distribution anything so long as it covers the expert policy. So I can basically have a large amount of suboptimal data. And I would actually think that's a good idea because basically that data means you don't have to like retry and have the same mistake over again. So you actually can see that bad things happen when you kind of go off the path. This will be really good for you. So I actually think it's a very natural, like resets are actually a really natural way to use kind of suboptimal data. Yeah. Other questions? Cool. Okay. Now I'm going to talk about hybrid training. And if you have a bit of an RL theory background, I'm basically minimizing the sort of two-sided performance difference lemma style things that like Teng Yang and Nan are particularly big fans of. So, kind of going back to our schematic kind of depiction of adversarial, right? We effectively have this sort of like, outer loop and inner loop. In outer loop, we kind of pick our word function via classification, and inner loop, we optimize it via reinforcement learning. And sort of, as you can see from this picture, we're kind of ignoring the expert data during this RL part, right? We've just used a pick reward function, and then we're doing policy optimization kind of from scratch. And the idea of hybrid training is actually very simple. It's that I'm simply going to also train on my expert data. So let's say I have like an off policy RL algorithm where I can kind of train on whatever data I want. This should seem fairly natural, right? Because usually for inverse RL, you get told that whatever you did was wrong, because I'm just trying to compare you to whatever the expert did. But here, I'm also giving you the positive examples and not just the negative examples. So it makes it kind of easier to figure out what to do. So I'm going to go through a particular example of this. I'm going to go through an algorithm called HiQ, which is due to my brilliant lab mate, Yuta Song. We're going to basically try and solve this problem via, this particular procedure. We're going to have some Q hat. We're going to initialize it to be 0 everywhere because, why not? And I'm going to basically execute the greedy policy under Q hat at each iteration of this procedure. And I'm going to do tie breaks arbitrarily. So right now, everything is 0. Everything is tied. So I'm going to kind of pick a random path to my tree. So I might go this way. Well, everything's still 0. Okay. I'm going to have to pick another random path to my tree. I'm going to do this, still 0, 0, still, 0, still, over and over and over again. What if I also fit this Q hat on data from my expert, right? Then what I would see is that at state S2 here, if I took action left, I get reward 1. So this means if I back up a time step at state S1, if I took action left, I'm capable of getting reward 1. Same thing at the sort of top here. And that means that my argmax policy is not going to be the expert policy, right? So what this is basically doing is it's also giving me sort of the positive examples. So it makes it a bit easier to figure out what to do. And when you try this out on Majoko, this actually works better often sometimes in the reset idea. I don't think this is like a fundamental thing. I think this is maybe just an artifact of the problem. But for intuition for why this is true, for this sort of like filter reset thing in purple, I'm only using the expert states during policy optimization. But here for this hybrid training, I'm also using the expert actions. So I'm using strictly more information. So for problems where you actually have access to expert actions, like you're not loading from videos or something like this, I think this is like, you might have to stick with this. But if you do have access to expert actions, this is a pretty natural thing to do. So you get sort of this kind of performance boost from that. Yeah.
So like, do you pre-train the Q value using particular iterations from the expert data?
So no pre-training. What I do is that when I am fitting my Q function, I sample a batch of data, half from my learners replay buffer and half from the expert demonstrations.
I see.
Yeah.
Like, why don't you do the offline part for the expert? You do like 52 iteration or something like that to pre-train Q value for expert data and do some online.
Yeah, I mean, I think that'd be a perfectly reasonable thing to do. It probably went well. I wanted to sort of show that if we'd be training from scratch, we still get a speed up here. But in practice, I would probably do what you suggested. But then still, though, once I'm actually learning online, I would still want to do this sort of like mixture update. Yeah, right. Yeah. Yeah.
will this practice cause a distributional shift? Because it's a very common problem in applying reinforcement learning. They use data from other policy to train.
Yeah. So the sort of magic thing here is it won't, because I'm still doing online RL here, right? I'm just running on this mixed kind of batch of data. So this is broadly speaking an idea called hybrid reinforcement learning. And the core idea of hybrid reinforcement learning is I want the guarantee of offline RL that I can compete with the policy covered by the offline data set. But, you know, I still want to be robust to compounding errors, things like this. So I'm going to kind of trade on this kind of mixture distribution. And you can prove rather rigorously that this actually does work. Yeah.
To do this kind of training, you need reward signals both in demonstration and also you need that from simulators, right?
Right. So none of these algorithms get access to reward information. I'm always adversarially picking a reward in an outer loop via classification. Yeah, there's no reward information here whatsoever.
Okay.
Yeah. Yeah.
Just to confirm, like, you are not, we are just using the expert demonstrations that that's available. You are not, and not querying on any.
No. There's no queryable experts in this talk. No. If you can query the expert, that's great, and you should do it, but usually you can't. Good questions. Any others? Yeah.
So what are you plotting on the y-axis? Like, what's the actual like score function?
Oh, yeah. So for each of these tasks, there's some sort of like ground truth reward function. And we basically train the expert policy via doing reinforcement learning on that reward function. And I'm basically plotting the performance under that reward function. Yeah. So it's some combination of maximize the amount of distance you travel, subject to some sort of like control penalty.
So you're updating your discriminator during policy training as well.
Yeah.
Right?
Basically each like kind of step in here is a new discriminator I've chosen. Exactly. Right. Yep. That's kind of how we avoid actually needing to have reward data here.
Have you tried to compare with SQI?
Yeah, so Squill will like has this sort of interesting behavior where yeah, I don't want to get too much into this, but in essence it will go quickly up and then crash back down because you basically are labeling everything the learner does with the word 0.
Yeah.
So even once you're doing well, you're going to eventually start failing because even once you start exhibiting expert behavior, you still tell yourself you're doing everything wrong. So you actually want to do this sort of like iteratively picking a reward function thing. There's variants of this that you can do that I don't talk about I'm not going to talk about today that essentially there's like a correct version of Squill you can do that like doesn't require explicit learning a reward model, but doesn't cause the sort of payoff. It's very simple. It's basically instead of doing like 1 and 0, you do 1 and like -1 over k as the reward for the learner. This has a really nice interpretation as just being a functional gradient, and it works quite well in practice.
Yeah, thanks. So why does method does not suffer from the instability of game like training style? Because when your policy is good enough, the discriminator could not differ, right?
Yeah. So and then then basically I mean, in essence, right, I'm doing a bunch of things here to like, stabilize like training the usual way you would do for GANs, like in terms of learning rates and adding in like various penalties, like gradient penalties and things like that. So in general, I found that you can very directly just import whatever people do in GAN training over to adversarial, and it usually works quite well. Yeah, good question. Other questions? Thanks, and I really appreciate all the questions. I've like given like this kind of talk before, and these are by far the best questions I've gotten. So thank you. Okay, so now let's talk a little bit about hybrid model fitting. This is an idea due to Ross and Bagnell from 2012. There's a really long performance difference lemma I could write out here, but I couldn't fit it on this part of the slides, so I didn't put it. You can read the paper, or you can ask me for the link if you're curious. So kind of to the question you were asking, we have this whole idea of, doing resets, and that's kind of cool, but this can be kind of annoying if we can't do resets in the real world, which we can't, right? Like you can't like reset halfway through a backflip. So we're going to do the following thing instead. We're still going to do rollouts in the real world for picking a reward function in our M star, but we're going to do all policy training via model-based reinforcement learning in the model. So because I've just like learned the model, a dynamics model, I can just reset to whatever state I want, right? That's just the initial state I pass into the model. So you can kind of run this algorithm in the model. I'm not going to focus much on computation. I'm going to mostly talk about like, well, given we actually are you know, trying to fit this model, how exactly do we actually want to fit this model? So I think perhaps the most like first pass thing you would think of doing would be fitting a model that's accurate just on expert states. And if you think about it, if I'm saying, okay, I'm going to always reset you to expert states, it seems kind of reasonable that if you're accurate on expert states, you'd be fine. But it's a bit tricky, right? So let's say we fit a model that looks like this. You know, it's accurate on the expert states, it always kind of gets the right place. But it just says if you take the other action, you automatically just, you know, pass through a wormhole and teleport to the goal. Like your model can kind of do whatever it wants, right? Because you never actually trained on that action because the expert always goes left. So this can kind of lead to weird things where you have an overly optimistic estimate of how good your policy is in your model. It's kind of like a common problem in model-based RL. So we would, if we were trying to actually compute a policy in this model, we pick this one here, and we're not going to pick the expert policy. So the kind of fix here, as you can probably guess, is we're going to fit a model that's accurate on both the expert and learner data. So this way you both kind of see, you know, if you were to take the right actions, you'd end up in the right place. But also if you were to take the wrong actions, you observe that there are actual negative consequences to what you did. And you need basically both of these properties to ensure that you do well. One other thing I just wanted to point out here is that the fact that there's like not the other half of the tree here is not just because I was lazy. It was because I actually wanted to make a point that nowhere in any of these proofs am I assuming I have a globally accurate model. I'm only assuming I have a model that's accurate on the expert data and on my own policies distribution, which is a much weaker requirement. Right. I think having globally accurate models is like a thing maybe you could try to do in self-driving if you can pay a lot of people to like build a whole simulator for you. But for like things like household robotics, I think that sort of locally accurate models are a much more reasonable requirement. And if you do this, things get even faster. So we sort of ran this algorithm for 1/10 as much time as all the other algorithms just to kind of point things out, but you can pretty quickly just shoot up the expert performance, which is like 1/10 of the amount of interaction. I'm like particularly excited about this algorithm. I think it's like the right way to do a lot of like robot learning in the real world. But yeah, it's in essence running this purple algorithm filter, but inside the model. And because we're not actually paying in terms of interaction when we're doing like things here, the sort of x-axis scaling is much nicer. And we've also tried out these algorithms on these like harder ant maze tasks. And what you'll see here is that, you know, kind of naively doing resets or standard inverse RL don't work. Doing just hybrid training gets you a little bit off the ground, but it doesn't like, you know, really work. You're still doing worse than behavior cloning. But it's when you combine it with, you know, hybrid training and resets, you get kind of nice performance. Or when you do hybrid training and resets, but in the model, that also works very well. So my point here is that these ideas are not like independent. You can kind of stack them and combine them in various ways. And oftentimes kind of stacking them all together seems to work the best.
Why have you hyper become so stable?
Oh, so this is just because we ran it for less time. Yeah, I just wanted to show that we could match the performance with less time. Yeah, good question. Other questions? Cool. Okay, so that's kind of what I wanted to say about imitation. And now I'm going to talk a little bit about RLHF. So this is going to be a bit of a context switch, but I think you'll notice I'm going to basically use a very similar set of tricks. Right, so in RLHF, right, we get sort of preference labels from people who say, you know, hey, I prefer you doing A to doing B, and you know, I want to learn this sort of maybe like a language model chatbot, maybe like a policy for controlling my like assistive walker that sort of like, you know, reflects these preferences. So I'm going to give you maybe like a description of the way people usually solve this problem. I'm going to then argue that this has like some reasonably deep fundamental flaws. And then I'm going to actually show you how we can fix those via a little bit of clever game theory. So let's say we kind of think about the way this usually gets done. And if you've heard the term preference-based RL, same thing as RLHF, just things get renamed. So we get some data set of, I prefer generation 1 to generation 2. I'm going to train a reward model, aka a classifier, between these two things. And I'm going to do RL with this. So I'm basically going to, sample trajectories our generation policy, scrape them with the reward model, and then do RL with that. And this is sort of what I would call the offline setting, where I just have an offline data set of preferences. There's sort of the online setting, or what I'm going to call an online oracle, where, what I do instead is I, sample a bunch of things from my policy. I query my human or my supervisor model for like their preferences. I use that to train a reward model kind of online. And I use that reward model to sort of label my data and do RL with that. So you should think of this as looking very similar to inverse RL, right? The only difference is that in inverse RL, I always assign the expert to be the positive label and the learner to be the negative label. So that's kind of like the usual setup for things. Before I talk about the problems and stuff, are there any questions about this kind of usual thing? If you've seen like any of these ChatGPT LLM papers, this is exactly what they're doing.
I always have a question for RLHF for language model.
Yeah.
Why is it not a contextual bandit problem? In the sense that it seems like your reward is always sparse. Like you wait the sentence, right, to finish, then you get a reward. Like, can we just use like contextual bandit like to solve this?
Good question. So I mean, it's a contextual bandit with like an exponentially large set of arms, right? And I think oftentimes just treating that as a search problem ends up working better in practice, right? This is like, before like John Langford's like learning to search stuff, that was essentially the trick, right? I don't think it's like fundamentally not a contextual bandit though. Other questions? Cool. And the issue here is due to a little known fact, which is that people disagree with each other. So I'm gonna give you guys a very cartoonish example here, but trust me, like the real problem is much worse than what I'm saying here. So we're gonna have three groups of people, and group one is really gonna prefer, rocks to scissors, and we're gonna say they compose a fraction A of the population. Group two is gonna really prefer paper to rock, and they're going to be, fraction B of the population, and you can probably guess what group C feels like. And okay, the sort of thing I want to emphasize here is that each of these groups have completely consistent preferences, right? All of these people really believe this is better than that. All of these people believe this is better than that. The issue is going to be when we sort of aggregate preferences together. That's where problems are going to start happening, right? So I'm going to make this slightly more mathematical, and I'm going to basically represent those preferences as like a matrix. So this matrix is basically going to be, how much I prefer the row to the column. So it's going to be +1 if I always prefer it, and then -1 if I never prefer it. And then, down on the diagonal of these matrices, they're always going to be 0 because you can't prefer something to itself, and they're going to be anti-symmetric because, you can flip the order of things and that would give you the opposite. I can do this for all three of these here. So this gives me, these sort of like three kind of matrices. And then let's say we actually wanted to aggregate these together, which basically means we take each of these matrices, multiply them by the proportions, and sum them together. We get a matrix that looks something like this. And I want to point something out here. There's no reward function that can actually explain these preferences, right? Like, because this reward function would simultaneously need to say, like, the reward of rock is better than the reward of scissors. The reward of, scissors is better than the reward of paper. The reward of, paper is better than the reward of scissors. So the first and the third conflict. I can't have both of these at the same time, right? And another way of seeing this is that, let's say I say A, B, and C are equal. So that's 1/3, 1/3, 1/3. You can say there isn't a row here with a unique highest sum. And the sort of point I want to kind of emphasize here is that this problem is not just like an issue with this sort of like weird thing I've constructed. This problem only gets worse when you have a larger set of options, right? Because you would need everyone, at least the majority of people, to agree that one option is preferable to all others. So think about what this means for language models, right? It's saying that I think the majority of my population of raters think a single string in the space of all natural language strings is preferable to all other natural language strings. That is entirely nuts. And if that doesn't just seem nuts to you, right? If you actually look at any of the data from these sort of like RLHF things, right, they're incredibly noisy, right? Like people can't even agree on like helpfulness versus like safety. They are not gonna be able to agree on just like there's one string we agree to all others. So that is sort of the problem here. I'm gonna now try and argue about a solution, but any questions about the problem first? Cool. So I'm gonna kind of pick a pretty reasonable thing to do here. And let's say I instead of picking a single, thing, a rock, a paper, or scissors, let's say instead I said, okay, I'm going to pick rocks 1/3 of the time, paper 1/3 of the time, scissors 1/3 of the time, right? Then notice that this is as preferred as any other policy, in the sense that I could pick any other distribution over rock, paper, and scissors, and I wouldn't prefer it to this distribution, right? And if you have a bit of a background in game theory, you know that this is the Nash equilibrium solution to this zero-sum game, and that's exactly what it means to be a Nash equilibrium. So a bit more formally, this is called minimax or von Neumann winner. Minimax is a term from the social choice theory literature. The earliest reference to this I could find was like in the 1960s. In the contextual bandit literature, this is sometimes called the von Neumann winner. Thanks to Mira Dudick and folks. So it basically says, let's do this here. So I'm going to try and solve this two-player zero-sum game, policy pi1, policy pi2. And what I want to do is basically pick a policy that generates trajectories, samples that are preferred to the other policy generations. I'm ignoring context here, but you can add context in and it's the same thing. But this is sort of like the notion of kind of a rationality I'm kind of going for. And this is different than what is usually called a Copeland winner, which is basically the solution you'd get from the word-based RLHF, which is basically saying, okay, I want you to look across all other policies and pick the one that kind of has the maximum row sum of that matrix. So the sort of key thing to note is that via the sort of like standard game theoretic arguments, we know that this solution concept always exists. But here, there's no reason to believe there's a unique Copeland winner, right? There's no reason to believe there's a unique string in the space of all natural language that the majority of my raters believe is preferable to all others. So I think there's at least 3 reasons you prefer the first concept to the latter. The first is that it's guaranteed to exist under the usual conditions for like Sion's minimax theorem. And another thing that is actually really cool here is that, right, if there is an optimal policy for your problem, like if there is a reward function that explains the preferences, the minimax winner and the Copeland winner will be the same thing. So this is a strict generalization, right? So like it is robust to intransitive preferences when they exist, but if for whatever reason your preferences are transitive, there's no cost in actually trying to think about it this way. Because if there is like a best option, the Nash equilibrium strategy is to always play that option. And I'm not going to get into this, but there's a variety of sort of like nice consistency properties, like merging data sets that agree on a minimax winner cannot change the minimax winner, which like a deterministic option like the Copeland winner can't satisfy. Okay, so that is maybe a solution concept that's somewhat interesting. Then I'm going to maybe make a statement that is hopefully not controversial, which is that multi-agent reinforcement learning is hard to scale. So we think about this game, right? And let's say we think about language models. That means like this player over here is a language model. And that this player over here is also another language model, right? And then I'm doing adversarial training between these 2 language models, right? Like this stuff, this sort of like adversarial training way of solving these games was really common back in like the bandit days when people are trying to solve, small problems. But if you think about trying to do this over like these gigantic models, right? Like I don't even know if you can store both these models in memory. And then you have to deal with the optimization dynamics of this sort of multi-agent problem. Not fun. So when we were thinking about this problem, we had a question, which you will probably be able to guess the answer to. And it's like, do we actually need 2 players to compute a minimax winner? And the answer is no, because our game is entirely symmetric, right? There's no difference between these 2 policies and their payoffs. This means that there will be a Nash equilibrium such that both policies are equal to each other. It will be a symmetric Nash equilibrium. So this means that rather than doing this sort of adversarial training, we can instead do game solving entirely via self-play. I was pretty proud of that transition. So you might ask, okay, what does self-play actually mean here, right? And it just means that rather than having 2 policies, you just sample 2 generations from the same policy. And effectively, that's sort of like your fictitious second player. And I'm not going to get into like a lot of the theory of this particular thing in the few minutes we have left, but there's actually a bunch of reasons this is nicer than the usual arguments for self-play. Usually for self-play, you can only make an asymptotic convergence guarantee. But here I can actually argue that you inherit the rate of your underlying Navier algorithm, which is very cool. So we have an algorithm we call SPO, or self-play preference optimization. And basically what it does is it tries to optimize effectively this reward model, where you have kind of a sequence of reward models where the value of a trajectory is in essence how often it is preferred trajectories from the last policy. And what you can show is that basically if you have a no-regret algorithm of your policy class and you run it on with this sequence of reward functions, you can compute an approximate max winner at the rate of the underlying algorithm. And I think this is really nice because this gives us a general reduction of computing minimax winners to online learning, which is very cool for a variety of reasons. Slightly more practically, perhaps, if I pick a particular no-regret algorithm, specifically natural policy gradient, you can prove that you get this sort of like regret rate. And if you've heard of things like PPO and soft actor critic, these are really in some senses approximations of natural policy gradient. So I think you can pretty reasonably say that this gives you a reason to believe this sort of thing would actually work. So slightly more practically, let's kind of go through the flavor of how you would actually run this algorithm. So I'm going to have my policy. I'm going to sample multiple completions from it. I'm going to ask my human rater or my preference model, which do you prefer? And I'm going to basically set the reward to be the win rate of those comparisons. And then I'm going to do RL with those kind of like win rate rewards. And this seems like it requires sort of an online oracle. But what you can imagine is basically if you have an offline data set, you first train a preference model, where you take in both trajectories as input, and then you output a score, rather than a reward model where you take in a single trajectory. And then you basically run the same algorithm I just described. And sort of comparing this to the kind of reward-based algorithms, right? So in the offline setting, these are really similar. I'm just training a preference model instead of a reward model. So something that takes in both strategies as input rather than one. And I'm using the win rate as the reward rather than just using the score from the reward model. In the online oracle setting, I'm basically completely avoiding sort of going through a reward model bottleneck here because I don't need to. I can just optimize directly based on the win rates.
I understand another benefit is you don't rely on the utility function, the preference reward model learning. Still, you always need to set up the exponential, the Boltzmann style.
Yep. I'm not making any assumptions that there is an underlying utility function that some sort of Boltzmann maxent thing. I'm not making any assumption whatsoever. Like nowhere in any of the derivation of this algorithm did I assume anything about how the preferences were generated, right? It's actually quite nice in that sense. Like I think this is like a strict generalization of the reward-based things. And because minimax winners and Copeland winners are the same thing when there is an underlying reward function, I will actually recover the same thing in those cases when there actually is an underlying function. So it is like a strict generalization. So we are getting reasonably close to time. So I'm going to go through the results relatively quickly. So we first tried it out on some problems with intransitive preferences where we're trying to aggregate several subpopulations. And the star here's the minimax winner. You'll see SPOs, they will pretty accurately compute it. But something that looks like standard RLHF or with a reward model basically picks the corner that's closest to the minimax winner because it can't actually deal with this sort of distributional thing. We also tried like a somewhat complicated and contrived Majoko problem where we effectively want you're like an ant-like agent walking along a plane. We basically want you to stay a certain distance from the origin, and then we want you to basically I think about it as the crust of a pizza, and we want you to basically you lose to the slice that's ahead of you. So basically the kind of equilibrium strategies play uniformly over the crust, and you can show that you can actually compute that, which is kind of cool. One thing here that I think is actually somewhat surprising to me at first is that if I compare, so RL here is with actual access to reward. If you compare like the SPO algorithm to reward model based approaches, one thing that's actually kind of interesting is we're often faster, even when there actually are transitive preferences. And we were a bit confused about this for a while, but it turns out you can prove that if you have like a clean underlying utility structure, usually when you're doing game-theoretic algorithms, you have to pay with a slower rate for dealing with adversarial robustness, but you actually inherit a fast rate here. And it's like a somewhat non-trivial proof, but it's in the paper if anyone's curious. So we actually, even in the cases where you would sort of expect reward-based and reward model approaches to do better, we do like better across the board. We're also more robust to like stochastic preferences. Stochastic here meaning I flip the preference with some probability when I get the label. Still seeing it across every environment, we can basically optimize pretty well. And even up to like, preferences that are like, at least in some environments are like flip with like 30–40% probability, we can still optimize super well, which is actually like the levels of disagreement you see in practice in LLM data sets. So that's kind of cool. We also tried running it on some sort of non-Markovian thing. I'm going to skip that for right now. Last kind of result here that I think is kind of cool is that, so after we had proposed this algorithm, some folks from DeepMind ran algorithms that are essentially really similar to what we had proposed on some various fine-tuning things, and they were able to actually share their results. Turns out it works pretty well. So if you're in the online Oracle setting, something that looks like SPO ends up being preferred like 60% of the time by human evaluators, compared to like 6% for standard RLHF and 7% looks like DPO. And if you look at the offline setting where you first train the preference model and then do things, you'll notice that we're preferred over like SAT 90–80% of the time, and we're preferred over standard RLHF 75%. So this actually does scale quite well to real language model problems. So with that, I'm gonna go to my last slide. So this was a collaboration with a lot of folks here at CMU. That's me, my advisors, Drew and Stephen. For the latter half of things, this was a collaboration with some folks at Google Research, Alec, Chris, and Rahul. At Cornell, we worked with Gentile in undergrad and some Japanese faculty there. That's my email, that's my website. If you want to read the papers in greater detail, there are the QR codes if you want to scan them. But with that, I'd like to thank everyone for your time. I only went 2 minutes over, which I'm really happy about. And yeah, I'm happy to take any questions if anyone has them. Thank you.
Maybe we can have like a few big questions. Before that, I think it's maybe have a student. Could you explain what is DPO, the direct preference optimization?
Sure.
Yeah, is this very popular?
Yeah. So I think you can think of DPO as essentially preference-based behavior cloning. So what you do is you have a data set that looks like, I have this preferred to that. And I essentially say raise the relative probability of the preferred one to this preferred one. So it's just like effectively like you have a ranking loss and you just like optimize that ranking loss between these two options. So this is like a purely offline method versus the things here are actually interactive and like getting continual feedback over and over again. And that, this property of actually judging a model based on what it actually does rather than like some offline data set seems to be rather important in practice to get good performance, both in language models and in the real world with robots. Other questions?
Other questions?
Yeah.
So maybe this is a stupid question, but like if you're getting preferences from a giant group of people, like does SPO handle having inconsistent preferences? Like say multiple people are given the same query, but some of them A, some of them say B is better.
Yeah, exactly. That's the exact setting SPO is like meant to tackle, right? So like I tried to present it in the way there's like separate populations, because like I think like maybe you say there's multiple populations, all of whom are internally consistent, maybe not like a single person is internally intransitive, but that's still fine. Yeah, it's sort of like I'm making no assumptions whatsoever about the preference structure. And that's like part of, I think it's also like one of the things that's kind of like interesting here, right, is that like in classical like preference-based RL, right, you basically thought about getting all the data from a single person. So I don't think dealing with a sort of like social choice theory thing mattered as much there. But when you think about doing it at scale, you really do have to deal with the fact that people disagree. This kind of necessitates different algorithms, in my opinion. Yeah.
Impressive words. I'm wondering how does the advantage of your method over baseline behavior clone scale with the amount of data expert?
Yeah, good question. So I think that if you have a truly absurd amount of data, you're in a problem where you can recover from any mistakes and you have an expressive enough policy class that you can perfectly mimic the expert. Behavior cloning should work fine. But most interesting real world problems don't satisfy at least one of these. in general, you would expect that when you have very limited data, the interactive methods do better. Like more formally, they have tighter minimax lower bounds than the finite sample regime. But as you scale up the amount of data, I think you end up having to deal more with the fact that you have to, like, you will still make errors, but it matters where you make errors, and the interactive methods make sure you don't make errors that like kind of compound over the horizon, versus the offline methods don't have an ability to tell the difference. Yeah. Other questions?
I think we are good. Let's send the speaker again, and yeah, if you have questions, raise your hand. Yeah.